you can. They got to dissipate their heat. Let's take a look at another example. So I've got hair. So I want to know which one is going to lose more heat quickly? Which one's going to lose heat more quickly and why? And this I want to just drop into the chat. Jackrabbit or snow hare? Jackrabbit or snow hare? Which do you guys think? Which one will lose heat more quickly? Drop it in the chat, yo. Drop it in the chat, yo. 5, 6, 7, 8, 9, 10, 11. That's 11. Keep it up. 29 of you. 17. Welcome, Cam. Old Jackie boys is what J.R. says. Okay, I got 21, 23. Wait on 6 more of you. Don't make me wait forever. How are we doing on time, Medlock? 24. Thank you, Medlock. Okay, so that's it. Thank you, guys. So out of 29 of you guys that answered, 26 of you guys said the jackrabbit would lose heat more quickly. So let's just look and see. The jackrabbit, very skinny. It's got these skinny legs, got a lot of surface area. And surface area is, think of surface as doors. If you need, think of what doors are ways you get in and out of things. So the more surface you have, the more opportunity you have to be able to lose heat. This one's got a large pair of testicles here. Didn't notice that till just now. So it's got a little surface area going on there. But it's got these long, skinny legs, these long ears. These ears aren't so much for hearing with this jackrabbit, having these large ears. They're mostly going to be related to dissipating heat. Again, you can see here veins and arteries in the ears, so that blood is going to get pumped to the ear, and then that blood is going to be coming from the interior of the body, and it's going to be dissipating heat. It's going to be getting rid of heat. And if you're a jackrabbit and you live in the desert, or you live in savannas or prairies, it's pretty hot. You can't escape the sun. Now, if you look at the snow hare, it doesn't have a lot of extra skin or long legs. It's got short ears. It has very little surface area. It tries to reduce that surface area as much as you can. And you want to reduce your surface area as well whenever it's in the winter. So your surface area really is your skin. So if you put on a coat and you don't expose your skin, you tend to stay warmer. It's all about the diffusion of heat in your body. And then if you can reduce the perimeter of your body being exposed, you can conserve that heat. They can't put on clothes. Animals don't have that kind of situation. So let's continue with surface area a little more. Use some other examples. Some of you guys have probably flown a kite. Some of you guys have probably have also been on an airplane or seen an airplane. So an airplane has, do you want to decrease your volume, you want to decrease your weight, and you want to increase your surface area so you can get wind or air under these wings to lift you into the sky. Same thing with a kite. You want to have a lot of surface area, very little volume, so you can be light enough that you can get the wind to get under these wings to keep you flying. Now let's think about this scenario. So let me see, who do I want to pick on today? I'm in the mood to pick on people. Medlock was fun. Let me pick on Tracy Tarleton. I don't like to pick on Tracy. Tracy, can you come on your mic? Tarleton, can you hear you? Hey, what's up, Tracy? All right, so here's what I'm going to do. You get to make some choices. Now, I'm going to give you an experiment. We're going to do a little experiment, you and I. So I've got a pot here, and it's going to be 100 degrees Celsius. Hot. It's boiling point. See that steam coming off of it? Now, this is soup as well, and it is also 100 degrees Celsius. This soup is in a cup, and this soup is in a pot. And I'm gonna turn off the heat. There's no heat coming into this. There's no flames coming into this anymore. We just turn this pot off. I put some of that soup into this cup. They're both right now at the same starting temperature, 100 degrees. I've got you with me, and I'm going to say, okay, Tarleton, I'm going to shove your hand into this pot or this cup in 5 minutes. Which do you want me to put your hand in?
The smaller one.
Why?
I mean, for one, the big one is like steaming. So
yeah, but they're both the same. They both have the same starting temperature.
Oh.
They both have the same. You're just gonna wait 5 minutes. Which one do you want? Which one do you think is gonna cool more quickly? The cup or the pot?
I still say the cup.
Okay, you think the cup? It's smaller. I'm with you. I'm telling you guys, you know more about this than you realize. That would be the correct answer. So which one has the greatest surface area compared to its volume? That's the next question. And I'm sticking with you. One is, they're both the same. And so while you're thinking about that for a second, Mia says one is boiling, the other is just sitting. They're both just sitting. They're both the same temperature, starting temperature. This is an experiment. We keep things constant. I'm not going to remember everything. The only variable that's different here, and this is to a couple of you guys go, oh, look, this one's boiling. In an experiment, everything's the same except for one variable. And this one's large, this one's small. The pot is large, the cup is small. And so coming back to you, Tarleton, which one has the most surface area compared to its volume, do you think? The large one or small one? I'm going to give you a little bit of help. You intuited, you knew, because you've been a person on Earth walking around for 17 years, that this little cup's going to cool down more quickly. And remember, surface area is equal to doors. So which one has the most surface area compared to volume? Doors allow things to come in and out. In this case, heat escaping. So which one would intuitively have more surface area than volume?
The bigger one.
Okay, so we'll come back to that and we'll see later. All right, so new question or new thoughts? And a lot of you guys, if you're chatting to me, I'm not going to be able to look. And Precious, she's pointing out, Precious, like, oh, it's not constant because the pot is metal. Yeah, I couldn't find a metal cup. I thought of that, Precious. That's a good point. But we're going to say everything's the same except for small in this example. Just trying to. But that's a good observation. So I've got, how does this relate to cells? So we looked at big things. We looked at a pot. We looked at airplanes. We looked at some machines. We also looked at animals. But think about cells for a moment. So diffusion and osmosis, does that cost us energy? Does it cost us, do we have to use energy for osmosis and diffusion to occur?
No.
No, it's free. It's like a free service. It's like a delivery service like Uber Eats that brings you food without charging you. And you're just like, awesome, bring me food. I don't want to pay that. So molecules have to be able to get in and out of a cell quickly. Some of the things that go through cells with diffusion are water, which we have to stay alive, oxygen, which our cells, not all cells, but our cells have to have oxygen to stay alive, and then glucose as well. And we have to have glucose for energy. We break down glucose through cellular respiration to get energy. We don't have to pay for their delivery. They are delivered to our cells free. Now, what if you were large, if you were big, like this pot, it's going to take, I think I can get back to it. Maybe I can't get back to it. I guess I can't. If I'm this big pot, and I'm sorry, Tarleton, this one has less surface area related to its volume, it's going to slow down diffusion. Most of you guys who have ever cooked anything know that if you have a pot on the stove and you cut off the heat, you better let it sit there for an hour or two before you start to fool with it, because it's going to be hot as the son of a gun. You put food in a little cup, it's going to cool down really quickly, and therefore Tarleton's like, I think the cup, don't put my hand in a hot soup. It's going to cool down more quickly. So if I'm a cell, I better stay small. So do cells grow? Think about Mr. Sheen. Mr. Sheen is the qualifiers for life, the MRSHENG. Do cells grow? Are cells alive? And if they're alive, does everything alive, does it have to grow? Drop it in the chat, yo. Drop it in the chat, yeah.
Wait, can you repeat your question?
Well, remember the qualifiers for life. Mr. Sheen is going to be the characteristics of life, the things that qualify something as being alive. Well, are cells alive? Yes or no, Elosa? Are cells alive? Yes or no, Elosa? I think that was Elosa. Yes. Okay. Yeah. And all of you guys are now. I've got everybody. So and a couple of you guys said cells are not alive, and they are. Cells are alive, and cells do have to grow in order to meet the qualifiers of life. They do, but do they grow large? And that's the better question. Do they grow large? So I've got a bunch of you guys who are already answering this question, and let me get Jalen to come on. So Jalen, how do cells grow? Jalen Clark. If they don't grow large, they do gain a little mass when they divide. If they don't grow large, how do cells grow?
They mainly grow in numbers.
Yeah, they grow in numbers. That's right. They can't grow large. If they grow large, they lose the free service of diffusion and osmosis. And we got to go with free. I'm taking free every single time. Every single time I'm going to take free. So let me go away from this for a moment. Stop share. I'm going to bring up another document. And you guys, how am I doing on time, Ashley?
We got like 12 minutes and 52 seconds.
Jesus, man, we've got to hurry up. God, you're putting the heat on me. Quit stressing me out, Ashley. Quit stressing me out. I ain't got time for that.
Hey, I'm just
All right.
telling the time.
Okay, all right, fine, whatever. All right, now, I'm going to give you some other structures you're not familiar with. So the coronavirus actually attacks this organ in people's bodies that's killing them. So this is the alveoli. These are little bubble-like structures that are in your lungs. If you've ever felt a lung, they feel like sponges. They're really spongy. And they've got all these little hollow organs called alveolus. An alveoli, a singular one, is this. So this is a macro, a big example of it. If you were to cut open a lung, this is what it would look like. And then maybe I can bring some lungs and preserve them for you guys to look at next year. But I have this big alveoli, or this alveoli, which is a singular form of this little bubble. Notice it's really got a lot of thin structures, a lot of very thin structures, very thin, low volume, high surface area. And look at these capillaries and arteries wrapping around it. This is a nephron, and these nephrons, when we get to A&P, we'll study these things in detail. This nephron is how you make TT. This is literally how you synthesize urine. Very thin, low volume, high surface area, so diffusion and osmosis can happen really quickly. This is it in a very microscopic detail. If you look at the inside of these, they even have little folds in them to increase the surface area, kind of like the camel's hump. And that will increase the surface area to allow diffusion to happen really quickly. Let's look at a couple of others. So this is your small intestine. You eat, and you're going to absorb your nutrients. So you'll digest, you'll have catabolic reactions that will break down polysaccharides into monosaccharides, proteins into amino acids. And those are small enough that both active and passive transport are going to pull them in. So I'm going to zoom into this. That is it, zoomed in. Lots of surface area, very little volume. Lots of these little folds. And there's even microvilli on top of that, little bitty tiny ones on top of this little. So you increase it. The capillaries in your body, this is a major artery and vein, and then they go out from a vein, from an artery to what we call capillaries. They get very thin, and this allows blood to deliver oxygen and nutrients and get rid of CO2 that's in your muscles and get them out of your body, take it back to your lungs to breathe out CO2 and take in more oxygen. But very thin structures. Your neurons have very thin structures called dendrites and an axon. This is your axon, and this is your dendrites, but the same thing. You can see this, I'm zooming in on this part right here. Very thin structures. And so diffusion is going to occur and allow molecules to pass in and out that changes an electrical charge to allow this to work. So this is also going to be very thin as well. So let's do a little math. I have an example here. This is a vole, looks like a little mouse. They're native to here. There's a bunch of them on campus. I can show these to you next year when we do some studies outside. But this is its food. This is what it's going to eat in a week. And so I've got two situations here, two problems. And I want you guys to use your calculators and make this calculation. This, I will call on one of you to do this one of you to do this one, and one of you to do this one. So you want to do all three. So this is the food that it eats in a week. It's 175 grams. The vole itself is going to be 30 grams. So it's 175 and 30 grams for the vole, 650 kilos for the rhino, and the rhino weighs 1,900 kilos. So I want you to find X and find Y, and then let's find this one as well, the last one. So it's X divided by Y. And I'll give you guys, say, I don't know, 1 minute, and I'll take answers for all three. I'll call on 3 people. Ooh, you're texting me answers. Quit texting me answers. I'm going to call on somebody, yo. Who is going to be the next kid on the Pope is right? What do you solve? One of you guys asked what you solve. You're doing this right here. You're going to take the mass of the food eaten in a week for the bowl. That's 175 grams, and divide it by its mass, the mass of the bowl. So 175 divided by 30, 650 divided by 1900. That's Y. And then you take X divided by Y, and that'll give you how many times faster the vole metabolic rate is over the rhino, or maybe it's not. So let's go to the first contestant on the Pope is right, and that's going to be Taylor Tubbs. I feel like it's the Taylor Tubbs day. So Taylor, give us the mass, or not give us the mass, give us this number for X. How you take the mass of the food divided by the mole. What is X equal to? That's you, Taylor Tubbs. 175 divided by 30. What is X? Tubbs. 175 divided by 30. Everybody's waiting. Ashley, how much time do we have?
6 minutes.
6 minutes. We ain't got time to sit on our hands, Tubbs. Tubbs, if you do not answer, I'm going to assume that you're not there. And if you're not there, I'm going to bounce you out of class. I'm not kidding. You can watch the video later. 175 divided by 30. You can use your phone if you need to, a calculator. And 15 seconds, Tubbs. See ya. All right, let's go to Chavez. Chavez, could you tell me what is X here?
So 175 divided by 30, I got 5.83.
Okay, cool. Let's go for 5.8. I'm pleased with that. Me gusta. So let's go for the next one. Let's go to, how about we go to Medina Funky Cold. So we've got this one, which is going to be 650 divided by 1900.
It's a long one. Do I just round?
Yeah, you're round. It's gonna be less than 1.
0.4. Yeah, 0.34.
0.34.
0.34. 0.34.
Okay, so that's 0.34. So let me just separate that so people don't think it's point. We'll put that as 0.34. Okay, that's good. Now we've got to get to the last part. The last part's going to be pretty interesting. So I'm going to have to know x divided by y. So this is 5.8 divided by 0.34. Let's go to our good friend Aspen Jenkins. Aspen Jenkins. 5.8 divided by 0.34.
Say again?
What's the answer to that? So 5.8 divided by 0.34. That gives me my metabolic rate. What's the metabolic rate of my vole compared to my rhino? I want to know what's this vole got to do.
Well, I'm doing on a calculator right now.
All right, roger that.
I got 1.7.
Ooh, can't be. 0.58, I mean, excuse me, 5.8 divided by 0.34. It's got to
Oh,
be more than
0.4. Okay, never mind.
yeah,
I actually
0.34.
point in between the 3 and the 4.
Yeah, that's what I figured. Yeah. I may have even said that.
Okay, I got 17.0.
17.0. All right, so 17 times. So this is an important, cool number here. So like if I'm thinking about this, I'm thinking, what? Are you kidding? This vole's metabolic rate is 17 times faster than a rhino. Does a rhino eat more food in a week? Sure. They eat 650 grams of food. But to compare to its size, it doesn't. A vole eats a little bitty bit, right? Only 175 grams, but it's only 30 grams. It eats 17 times more food for its mass than the rhino. The thing about this vole is, what is it going to lose more quickly than the rhino? What does it lose more quickly than the rhino? What do you think it loses? Let's go to hairball. Hairball, what is the vole losing more quickly than the rhino? I don't know if Tabitha hears me. Yo, Tabitha, can you hear me? Hello? McFly.
I'm sorry. My headphones are really quiet. Did you say my name?
Yeah, I said your name. What is the vole losing more quickly than the rhino?
Did you say what is the mole losing more quickly than the rhino?
The vole, yeah, vole. It's not a mole, it's a vole. What is it losing more quickly than the rhino? Its metabolic rate is 17 times faster. It burns calories 17 times faster than the rhino. Why?
I guess it could be burning more energy.
It is burning more energy, but why? What is it losing more quickly? Actually, let me go back to your video. Where are you again? Let me find you on my list of kids. There you are. Cool. Here, put your head up to the camera so I can touch your forehead. Let me see. Okay, cool. What'd you eat for breakfast?
Water.
You had water. What did you eat for dinner? Let me try to feel your forehead again. Yeah. You're pretty warm. You ate chicken. Oh, you know that heat that I'm feeling from your forehead? I'm taking your temperature. Oh, do you have a temperature, kiddo? No, that is that chicken. It's literally chicken that got converted into heat. So if you think of this, if you ate everything that you've ever eaten, if you retained all that mass, you would be gigantic. We eat tons of food. Most of it is lost as heat. So this bowl is very small. So it has to eat a lot more food to stay warm. Food is going to equal the heat. Those are catabolic reactions. Remember, catabolic breaks. When you break, you release energy. Catabolic reactions are like fire. You release energy, and most of the energy is lost as heat. And so this vole is going to lose the heat more quickly than a rhino, so it has to eat more food compared to the rhino. It has to eat a lot more for its mass.
It's
Let's
the
do a little.
poke.
Yep. Time's up. Okay, so we'll take our data After everybody gets this data table copied down, and then we'll take our data from our experiment and see who was right. So everybody needs to copy this down in their notes. Everyone needs to have this copied down in their notes. This grid. And when you're done with it, you're going to show me a copy of it. That means you're going to have to come on camera. And if you don't come on camera, I'm tossing you. I'm tossing you from the class. So I'll give everybody let's say it takes 3 minutes. 3 minutes. You need to copy this data table. It's going to be 4 columns and 11 rows. 10 rows here, but you got to have a header. So they need this copy, including the formula that's written in here, everything that's written here. Copy that down, and when you're done with it, I'm going to literally go person to person to person, and they're going to hold it up and show me that you have it written down. Some of you guys are texting me that you're putting it into a Google Doc. If that's true, that's what you're putting it into, a Google Doc. You could take a picture of it with you and show me on your phone that you put it into a Google Doc. You've got 2.5 minutes. The next class starts at 11 o'clock. We have plenty of time. Sit, baby. Hey, Jalen, I like that painting behind you. It's a good looking painting. It's nice. Yeah. Okay, so let's go person to person to person. Tabitha, show me yours. Awesome. Elosa? Got it. Ashley Medlock. Excellent. Jalen. Yo, Jalen, you got to show me yours, yo. He's frozen. Oh, there he is. Thank you. Lopez. Thank you. Aspen. Woohoo! Tristan. Now remember, if you guys don't show me, I'm bouncing you and you can watch the video. Tristan. Excellent. Alan. Mark. Excellent. Mariella. Mariella. I'm going to bounce you if you don't show me. Coming right back. I'm going to go to Tracy and coming right back to you, Mariella. Tracy Charlton. Tracy. Oh, thank you, Tracy. Mariella, you got to show me your data table. That's what we're waiting on. In the meantime, Stein, show me your data table.
I already did.
Oh, sorry. Sorry. But Mariella, you show me now or forever hold your peace and bouncing. You got to watch the video. Deuces. Okay, gotcha. Earl, I got you. Thank you, Earl. So Emma. Uriel? I need to see the data table. Boom.
Say my name?
All right. Yeah, I said your name. I need you to show me your data table.
Oh, because you always call me Chavez.
Okay, Chavez. I'm sorry. Yeah, Chavez. I said it. Chavez. Show me your data table. Dylan, Juliana, Adrian, all of you guys. Just pop on quick, fast, and hurry so I can see them all. I need to see the data tables. We're going to be here till the cows come home. Okay, Adrian, Hirata, Reggie, Lazaria. Yep. I need to see data tables. Got them. Okie doke. All right, cool. We got them. All right, so here we go. Now let's take some data. Let's take some data and see what we got here. So I want to see what we get. And we're going to go over here, back over here, right? So I'm going to go back over here to my BioPope. I don't know if I can pin this and make it large. Maybe I can. That should be large. Everybody could see that, I hope. So I'm going to go and take these guys out. Let's see what we got. Most of you guys said small. Let's see what the data says. So I'm going to take it. You can see here, I've got water on the outside. Look at my hairy arms. I've got water on the outside and inside. I dropped some water on my scale, so let me get that off. And I'm going to dry it. And take this paper towel and I'm going to dry it off. Again, this is the large one. And then we're going to do a little math with it. Get it all dried off really, really well. Get this sucker all dried off. There's a lot of water kind of stuck in the edges of it right here in this little part. The water gets stuck. I'm going to dry that really well. And remember, we're just trying to find out how much water left it, not how much water stuck on the outside. So let's take the mass of it. So turn on the scale. It is 21.1. So let me write that down, 21.1. Where's the pen? Here it is, 21.1. All right, now we're going to do the small one. Check out the small one. And hopefully you guys got this point about it. We're going to do more of this. This is going to be a 2-day lesson. We got a short class today. Realize that the small one's going to lose weight more quickly, or lose mass more quickly. Whoa. Okay. 12.2. So it lost a lot more. So let me go back, share screen. And there's a formula here, and I screwed it up in the last class. So I need to post this video in a second, a different video. So the large one, we said started out, and if I can get this, and here's my formula, final minus initial. My final was 21.1 minus the initial, which was 21.5, and that is going to give me -4. -4. And that is going to give me, then times 100, it lost 4% of its mass. So that's -4%. It lost basically 4% of its mass. That's the mass that it lost. So let's go to the small one. Small one ended at 12.2 minus 13.1 equals, in this case, that is going to be 0.9 times, times 100. That is going to give me 9% mass. 9%. Now you think, oh, what's the difference between 4 and 9%? That's not a lot. Well, what if I do it this way? What if I take that 9 divided by 4? That is going to give me, somebody do it, 9 divided by 4. What is that number exactly? And what is that number, 9 divided by 4? So let's go to Ashley Medlock. Ashley, help me out real quick. I know I can hear you really well. What is 9 divided by 4?
It's 2.25.
2.25. 2.25. And to convert this to a percentage, remember you move your decimal place over 1, 2 times. So I'm going to convert this to a percentage that equals 225% difference. It was, osmosis was occurring in the smaller one 225% faster than the larger one. That's a huge difference. You think, 4% versus 9%, that's not a big deal, but it really is a big deal. It's 225% faster. That would be like the difference of driving 60 miles an hour to 100 miles an hour, or 130 or 40 miles an hour. That's a lot faster. So it was moving a lot faster. So you chose wisely, Charlton. You should want to put your hand in the small cup of soup because it's going to move. It's going to cool down a lot faster than a large cup of soup. This is going to be a lesson that we have to do over 2 days. When we come back, I do want you to have this table ready. We're going to need this table for the next lesson. I said -4, not -0.4. What do you, I didn't understand. Oh, you're talking about, oh, thank you. Yeah, that's 0.4. But again, I'm going to multiply it times 100. So it would be, that's still correct.
Mr. Pope, so we don't divide it once we subtract it. We don't need to divide it by initial.
I did. I was dividing it. Did I not divide it by this? Oh, hold on a second. You're right. So -0.4. Oh, you're so right. Thank you. Help me out. If I ever make a mistake, tell me I'm an idiot. So -21.5. What is that number? Sorry. That was wrong. Thank you. What is that number? -0.4 divided by 21.5. Thank you. Made a mistake.
I think 0.019.
0.019. So that's going to be 1, 2. That's going to be 1.9%. So that would equal 1.19%. Thank you. That's me being silly, which it means I need to do that over here. What is wrong with me? 13.1. So 13.1. What is that number going to be? That is going to equal what?
0.07.
0.07. Okay, so then I'm going to move that decimal over 1, 2 times. So that's going to be 7%. That's 7%. So then I need to take 7 divided by, thank you for catching my mistake. I'm trying to rush, 1.9. So let's go back. Since you're there, Alosa, tell me, what is that number? 7 divided by 1.9. That's even faster. It's going to be 300 and something percent. About 360%, I think. What is that number?
3.68.
6.8. So I'll move that over 1, 2. So that is going to be 368% faster. Thank you. That is 368% faster. It was happening a lot more quickly. 7% mass we lost in the small. 1.9% we lost in the large. It was 368% faster in the small versus the large. So yes, osmosis does occur more quickly when you have more surface area compared to your volume. And this will make even more sense when we come back. Don't forget these for the lesson for today and be ready to do some math when you come back. And always check me. If you stop the jump, anybody who can, if I make a mistake next time and you catch me, you get 5 points on the quiz and to the next quiz. Dang, Alosa's like, what? You could have, oh my God, I could have got 5 points today, but I didn't say it first. Now she's mad. If you catch me and I make a mistake, then 5%, you get 5 points on to the quiz because I'm human. All right, I'm gonna let you guys go. Hope you guys have a fantastic Wednesday and you get some plenty of baby sleep. And I will see you guys bright and early Friday. Adios. And we're doing this over 2 days. Some of you guys will, what about the live? We'll take it slow. Deuces.